Just a reminder, subscribe if you like these videos.
Strings, they make noise. Can we describe mathematically how they make noise? Well, you've probably heard of the wave equation before, which, is pretty basic, and it describes some situations pretty well, but for guitar strings, not so well. To model a guitar string, we're going to use the full, big wave equation in its true form. And we're going to solve it using Numba. We're going to assume someone plucks a guitar string, and we're going to solve for what the sound sounds like. We're going to make an animation of the string, and then we're going to make an audio file that describes what the string sounds like. All right, let's get to it. Okay, folks, let's solve this equation. So I have the equation here. There's a lot of stuff. You got to digest it. Perhaps important to talk about first is what everything represents. Y is the amplitude of the string. You have a string attached at both ends. Y is the height of it. And you can say at any point X, what is the height? There's T. T is time, right? And X is the location where you're on the string. C is the speed of the wave in units of meters per second. Gamma is the damping constant. And L is the characteristic length. And this looks almost like F equals ma. You're used to seeing that. If I move this second term to the other side, and you have this term that sort of represents acceleration, and then you have these three forces left over, it's accelerating based on the quadratic curvature, and then there's also a damping force, meaning it's being damped as it's moving along, and there's this stress-strain force that has another sort of constraint here in this problem. The string is fixed at both ends. That's what this says, at all times. At 0 and L, it's equal to 0. And there's an initial function at time 0 as well. And in order to do anything with this, numerically, we need to make it discrete. And this is the discrete form. And you might think, oh, you just made it 10 times more complicated. But I haven't. It's really simple. This J and M, you see that go with every Y. This lower thing is the position. So J says if I have a grid of positions and a grid of times, right? Because Y is a function of X and T. So it's like a two-dimensional grid. J is the, position, and M is the time. So I could set M is equal to 0, for example. And then I could go across all the J's, and that will be like freezing time and looking at what the string looks like. Or I could say I'm going to pick one position on the string. That would be like fixing J and saying, how does that evolve with M? And that would be like only focusing on one part of the string and seeing what that does with time. So J is position, M is time. And you might think, well, what am I going to do with that? Well, your goal is to predict the state of the system at a future time using past times, right? And I'll explain what I mean. If you solve for yj m plus 1, m plus 1 being the next time, because of course that thing is time, you get ym plus 1 is equal to this. You just solve for m plus 1 here. And you'll note that everything on the right-hand side of the equation only has to do with m and m minus 1. So it says at the next time, if you know everything at time m and everything at time m minus 1, you know all the information there, you can compute everything you need to know about time m plus 1. And you just plug it into this equation here, and you get everything you need. And furthermore, in order for this to be stable, so you're sort of iterating through time, you need to have this constraint c delta t divided by delta x is less than 1. That's just a mathematical fact, a numerical constraint that we have to follow here. So there's a lot of things. Pause the video, get used to it, read it over, try to make sense of it, and make sense of what we're doing here. We're going to be solving for this. And what this means is because we have ym plus 1 dividing on m and m minus 1, it means the first time we do this, so we need to have two positions of the string, because we'll be solving, say, we'll plug in m equals 1, and we'll have yj2, and then we'll have like y1, and then m minus 1 occurs as well, so m0. So we need that 0, 1 layer, and then the second layer is obtained using the first two layers. The third is obtained using the two layers below. Anyways, that's thorough, I feel like, what I've gone over. In terms of the parameters, typical guitar string length is around 0.7 meters. I'm going to say, so our grid of x points, there's going to be 101 points between 0 and L. So nx is 101. And this gives us delta x is 0.7 millimeters. I have to have 101, not 100 points. Think about that, right? 101 points is 100 intervals. The fundamental frequency of the guitar note, this is from first year physics. F is C over 2L. And an A note at approximately 220 hertz gives us the velocity of the string, 308 meters per second. So we know what delta x is. We need to obey this constraint above. So I set delta t as 5 times 10 to the negative 6 seconds. That satisfies that constraint. And if I want to get a multiple seconds of what the string is doing, so I'm going to choose 500,000 points for nt, right? 500,000 times 5 times 10 to the negative 6 is 2.5 seconds. Nt times delta t is the full time. And two parameters that I played around with that gave me a reasonable solution were L, the characteristic length here, at 2 times 10 to the negative 6 seconds, and gamma, just no units, and gamma is 2.6 times 10 to the negative 5, and this should be seconds per meter. That's the units for that here. So let's define our initial state of the string. This is when we pluck the string. Actually, I think before we do that, let's define our constant. So nx is equal to 101, and t is 500,000. L is 0.7. We got dx is equal to L divided by nx. Actually, dx, sorry, is L divided by nx minus 1. F will go to 20 hertz. C is 2 times L times F, first year physics equation. dt is 5 times 10 to the negative 6. L is 2 times 10 to the negative 6. And gamma is 2.6 times 10 to the negative 5. So these are the parameters for the problem. Now let's get the initial state of the string. So when you pluck a string, it looks like a triangle, right? It goes up to one point and then down. So here's an easy way you could do this, set this initial state. I'm going to say my first part is just a slope going up to a certain point. So I'm going to say this is empty.min space 0, 0.01, and 70. So if I just plot YA, I just get a line like this. Now I need to add the second part of the line. So by the way, 0.01 is the amplitude here. So for the second part, I could say YB. And I'm going to go from 0.01 to 0. And I'm going to have 31 points. So that I have those 101 X points that I need. And then Y naught, which is our initial condition, is the concatenate of these two things, YA, YB. And then I can plot Y naught. And I get, so I need this to be 31 points. And I get this plucking. So it's like you're plucking the guitar string at a certain location. By the way, this is sort of not really to scale. You know, really your string is long, so you could think of it as being like, yeah, something that looks more like this, right? And of course it'd be really, really long, so you're just, you know, pulling it up slightly. These plots in this video will be slightly not to scale. So anyways, we have Y naught. Now we need to create a 2D array of x, y, t. Now we're going to create everything and we're going to fill it with zeros. And we're going to start with that and then we'll slowly update it in the process. So our solution is like this, and I have nt and x. So it's just a big empty array. And this has 101 points, and this has 500,000 points. So now you see where our x's and t's are going to go when it's finished. So these are like, this would be like a snapshot of the wave at a given time. And then a column would be looking at a single point of the string going up and down. What we're going to do is we're going to set the first two rows of our solution equal to Y naught. So now if I look at solution, the first two are equal to Y naught. And you might think, why am I setting the first two? Well, you'll remember what I said before, that when I use this formula to update, time m plus 1, remember that each row corresponds to time. When I'm solving for this row here, which is m is equal to 2, 0, m equals 0, m equals 1, m equals 2, m equals, well, here m equals 1, so yj2, I need this 1, and I also need it at 0, right? If I'm solving for m plus 1, I need m and 0. So if this is equal to 2 here, then I need, this is equal to 2, then I need 1 and 0. So that's saying if I'm looking at this row, I need this row and this row. So the kind of hackish way to get around that is just to set both two equal to the same thing to start. Now we're going to use Numba to go through the iterative procedure. All it's going to do is it's going to say I'm going to go through this row, right? And I'm going to apply this equation for every point j. And I'll just extract all the points I need from the previous places, right? So this formula here, right? That's what I'm going to do. And yeah, so I've done this already. I'm going to move this just to be neat. Move this in this cell here. So now we have our solution like that. And this is how Numba works. And I don't want to type all this out. You can see I already have this pasted here, but I'll explain briefly how Numba works. So whenever I'm using Numba, right? Numba comes like wrapped with a Python function. So I have this Python function I want to do, and I'm going to wrap it in Numba, and Numba will speed this up by like a factor of 1,000 or 10,000 or something. So here's how it works. I put this at numba.jit here, and here is what I'm returning. I'm returning a 2D array. You can see this, of float 8. The input arguments are going to be a 2D array of float 8. That's this D. And then there's going to be 6 arguments. Some of them are integers, such as the number of times and the length are integers. And then there's going to be these four float 8s, which are dt, dx, l, and gamma. Make sure to set this no Python is true and no gil is true. So then it almost wraps that Python function. It says when this function is called, I'm going to use Numba, and I'm going to optimize this code in C. So compute D. All right. So how does this work? Well, I don't need this line here, I'm realizing, because I'm passing in length. So what's going on here? Well, I loop through times from 1 to times minus 1, right? So t starts at 1. And then I loop through positions from 2 to length minus 2, right? And so what's happening here, if I look at this formula here, I'm saying at the end, I'm solving for dt plus 1, right? So the first thing I do is I solve for this outer factor here. And if you look carefully at that, you should see that this outer factor is equal to this outer factor here. And then there's 4 terms on the inside here, right? 4 of these terms. And I have 4, P1, P2, P3, P4, right? And look what I'm doing. D is the array that I feed into it. So D is solution. I feed in solution, and I've already sort of crafted solution, so it looks like this. It starts at this, but it's not full yet. It has to iterate through. So I pass solution, and it will slowly modify it through each iteration. So it will set certain coordinates equal to things. So this, for example, D, T plus 1, I. This is this Y, M plus 1, J. Only J and I are different here. And then I extract everything I need from T. So it just says that the array at the next row, T plus 1, is going to be outer factor times all these, and I have these defined here. And because everything defined here only depends on T or T minus 1 stuff, I can go through that. Now, I is in range 2 and length minus 2. That's because I have this fourth derivative of position here, where I actually have positions that go minus 2, minus 1, plus 1, plus 2. So that's fine. Anyways, I can run this, and it creates this optimized function. And I encourage you to study this. There's a lot to explain here, but convince yourself that what I'm doing here and how I'm passing in a solution. So solution is going to be the argument D. can be convinced that what I'm doing here is I'm updating each row consecutively, and then I'm at each row, right? This is the loop over rows, and then I'm updating each position based on the previous rows. So convince yourself of that. So I have this. This is the most complicated part, by the way. And watch this. Immediately solved. So I pass in solution, right? So I'm saying sol equals compute d sol. So sol is the first argument. Sol was sort of empty. I filled it up, and now it's going to modify it more and more and more until it's done, right? I'm going to solve it for nt times 500,000 times, and x, which is 101. I pass in dt and dx. I pass in L, and I pass in gamma, right? So now I have everything. And so I can run this, and I get my solution. So here it is, my solution at all times of the wave. Pretty simple. So let's plot the string at some sample points. Let's say 500, and we'll plot maybe the 20,000th row. So here what I'm doing is I'm plotting certain rows. Remember that each row in sol corresponds to its freeze in time, so this would be like a freeze in time of the string. And so I can plot these. These are 2 sample times of where it's at. You know, maybe if I plot 10,000, it's at a different thing. So the string is wobbling around. But I want to create an animation of this because that's what's interesting. So you got to be careful when you're creating the animation, and I want to help sort of think about, well, you could create a GIF, but how fast is it going, and what's the frames per second and stuff, and all this. So if I take 1 over dt, right, I get this 200,000 here, right? That tells me that there are going to be 200,000 of these snapshots every second. So 1 second in real time is 200,000 of these rows, right? So it's 200,000 frames per second in real life. So if I only index every 10 frames, meaning if I go like this, I take every 10 frames, right? And now if I take the length of this, I should, oh, that's just this. It needs to be like this, start, stop, step, like that. And now if I take the length of this, I get 50,000. So rather than 500,000, I'm taking instead of taking every picture, I'm taking every 10th picture. So that would be 20,000 FPS because I'm skipping a bunch. And so if I choose a GIF where the FPS is 20, right, using this thing here, it means that our animation is moving 1,000 times slower than real life. So it's like you record it in slow motion and it's 1,000 times slower. Again, something to think about here, right? Convince yourself of this. I can explain it, but pause the video and meditate on this, write it down, think about it. And so let's animate it. It will take in the frame number I. And first let's set up everything before we define that function. We'll make a plot. I'm going to set the y-lim so that it doesn't go crazy when it's animating. And let's save the animation. Animation.func. Animation. .500 frames. Interval is 50. Again, interval not a big, huge argument here. Important. Interval is just something I set to default by 50. It doesn't really have to do with much. 500 frames. Right? And I'm going to say the way the animate works is I clear my axis, then I plot, and I'm going to plot, like I said, every 10th picture, every 10th snapshot I'm going to plot. So there's 20,000 frames per second. I'll plot every 10th snapshot, and I'm saving at, I'll just save an animation here. I'll call it string.gif. And I'll use pillow as my writer. And I'll save it at 20 frames per second. And I'm going to add this here as well. We'll set the y-lim. Alright, so the animation's finished. I can click on this, and here you can watch our string. So we initially plucked it, And you can watch it sort of do its thing. It's going back and forth. Remember, this is 1,000 times slow. The string would be moving really, really fast in real life, but this is like 1,000 times slow. This is what you would see would be happening with the guitar string. And remember that it would be stretched way out in X. It wouldn't be like this. But anyways, it's sort of cool. But for the cool part of this video isn't so much the animation, but making an audio file out of this. I want to hear what this sounds like, not what it looks like, right? That's the whole point of this. Let's create a wave file of the noise. Now you might think, how are we going to do this? We have this oscillation of a string, but I don't really know what noise that makes necessarily. Now what we can do is we can extract the amount of each harmonic at a given time. Remember that the first harmonic would be like a sine wave, second harmonic is another sine wave, and the function is built up of these harmonics. So using Fourier analysis, we can extract, well, how much of the first harmonic is there? How much of the second harmonic is there? How much of the third harmonic is there? And you can extract the amount of this by taking the integral of whatever it is at that time. So you take a snapshot in time, you have your string, and you integrate it with whatever sign of harmonic you're interested in, and that tells you how much of that harmonic there is at that given time. So here's what I'll do. I'll write a function. It's going to take in n. N is the harmonic, so I can plug in first, second, third harmonic, and at a given time, it will tell me how much of that harmonic is there. So first, let's make a sine array. This is just sine. So it's going to be n times np.pi times, and it's going to be np.lin space 0, 1, 101. Now this is n pi x over L. Remember that x over L goes from 0 to 1. So that's why I define this lin space. I don't need to put x over L, I'll just put this. So that's our sine array. And we're going to return an array. And it's going to return, this is an approximation of an integral, right? We're summing sine array times s for s in sol. So what this says is I'm going to loop through each row of my solution. Remember, the solution looks like this. And each one of these is a snapshot in time. And it's going to take, for each of this, I'm going to take the sum of this sine times this. And that's like this integral here. I'm not including dx, but it's proportional to that. By the way, this is what this means, proportional. I think there's a 2 over L literally there, but it doesn't matter. We're going to normalize it before we make the wave anyways. So it says I'm going to loop through all times, all rows, and I'm going to say how much of that nth harmonic there is, right? So I'll define this function, and then I'm going to see it. I'm going to call this harmonics, for short, HMS, harmonics. And I'm going to go like this. Okay, so what? I'll call this get integral. So what am I doing here? I'm using list comprehension. It's going to put in n is 0, n is 1, n is 2, n is 3. As a matter of fact, I don't need 0. That won't be important. But 1, 2, 3, 4, 5, 6. And it will tell me for each one of these harmonics how much oomph there is in that harmonic at that point in time. Because remember, the string could be bent in some weird way like this. And I would say, well, this is mostly composed of the first harmonic, and there's going to be a little bit of the second harmonic, etc., etc. So I'm saying, this is telling me how much of the harmonics there is as a function of time for each one. Right? So we'll let this run. This usually takes us a little bit to run. Okay, so that took about 30 seconds. So I have my harmonics. So what does that mean? I have a list of these arrays. I take my first array corresponding to my first harmonic, right? And I can plot this as a function of time. And I'll take, say, the first 100 points or so. Say the first 1,000. So what it says is that my first harmonic is oscillating like this sine wave. And if I plot 10,000, you can see that this is the behavior of my first harmonic. The strength of the first harmonic, or the amount of first harmonic that exists, is going up and down and up and down. Same thing with the second. It's sort of oscillating like that as well. The third and the fourth, etc., etc. You get this sort of behavior of it oscillating back and forth. Now, if I want the full sound, I need to add up those harmonics. So what am I doing here? I'm taking the solution. I'm determining how much harmonic that is in the first few. And then I'm adding them together to get a single time series. So I'm going to sum these together. Sum the harmonics. And I'm going to take every 10th point because it's sampled really highly, right? Delta T is really, really small. I don't need that much. So my total is going to be like this. And when I save it to a WAV file, I need to be careful that I convert it to np.float32. So remember what I'm doing here. I showed you all these signals here. I'm going to add them on top of each other, and that's going to build up a signal. Now I have my... I need to go like this. And put a bracket. So now my total series... and I'll take the first 1,000 or so. The first 1,000. And I get something that sort of looks like this, right? You get your waveform from your wave. So that works. Now we have that. Now we're going to make it into a WAV file. So, or this at the bottom here. I'm going to import two libraries, scipy.input-output. I'm going to import this thing called WAV file. And I'm also going to import from ipython.display import audio. These are the two libraries we need to make a WAV file. And then it's as simple as wavefile.write. I'm just going to call it sound.wave, 20,000 points, and I'm going to write tote to that. And if you want to listen to what you just created, you go audio, sound.wave. And you may be wondering, why did I put 20,000 here? Well, remember I showed above that dt is 5 times 10 to the negative 6. So if I go 1 over dt, that gives me my rate in hertz, which is 200,000 hertz, right? But I put 20,000. The reason why I put 20,000 is because I only sampled every 10th point. I don't need those higher frequencies. It doesn't matter. So that's why I have 20,000 hertz. You have to specify this, and then it will give you the right sound. And so now I can listen to my sound like such, and it will play a little thing here, and you can play it. And so it's sort of interesting, right? Now what I've done myself is I've created WAV files for a bunch of different notes. And so I'm going to read in the files that I've saved myself, like such. And with a little bit of manipulation, right? So for example, here, I'm going to add the A and the C together. And I'm going to add a little bit more of the C. So that's like playing a chord where you play the other note just a little bit louder. And you can listen to this, and I'll put it in the video. Not bad. Now here's something cool. We're going to do a little ending chord progression. So here I have my A and my C. What I've done here is I've delayed the C a little bit after the A C sharp, by the way, so it's da-da, da-da. And then I have a D, and this is a low F sharp. So it'll be da-da, da-da, and it will sound kind of cool. And I'm going to put a little bit more emphasis on this, so the notes are delayed. So it sounds like I'm strumming a guitar, strumming one chord after the other. So I can run this, and this is beautiful. Sort of. Anyways, here's what I want you to do. If you watch this video, you know how to do this. Create wave files for many, many different notes. Also, experiment with these parameters. Experiment with gamma and L. Find out what makes it sound the nicest, you know? I've found some parameters that seem to work and make it sound like a true guitar. But you can change these, and it will, of course, change the result. C, remember, C will change the pitch of the note. But gamma and L will change more, you know, fundamental things going on. The waveform in subtle ways that will make it sound like different instruments, for example. But it will always sound like a damped string. Anyways, I hope you enjoyed this video. If you made it all the way through, remember to like and subscribe. Thanks.